that there exists an real number somehow stuck. So there exists a real number R so that R squared is equal to 2. So this theorem can be, of course, generalized to any algebraic equations. Okay, let's try to see how to prove it. So to prove it, we'll use the completeness of the real numbers. All right, so first let's define a set. So let S be the set of all x's, the real number x, so that x is greater than 0 and x squared is greater than or equal to 2. So first, this set is non-empty. S is non-empty. So this is clear because the number, say 2 is in the set, since 2 is in the set. 2 is greater than 0, and 2 squared is equal to 4, is greater than or equal to 2, so S is non-empty. And second, S has a lower bound. Lower bound. So what is the lower bound? It's clear 0 is a lower bound because all the elements in S is greater than 0. 0. So the completeness of the real numbers tells us once a non-empty set S has a lower bound, it has a greatest lower bound. So Okay, by the completeness of the real numbers, there is a greatest lower bound. M for the set S. Okay, so first we'll show that M is greater than or equal to 1. First, we show that M is greater than or equal to 1. So why this is true? Because for any x greater than 0 but less than 1, x squared would be less than or equal to 1. X is less than 1. So that means all the x's in S cannot be less than 1. So any x in S is greater than or equal to 1. That means since M is a lower bound, at least the greatest lower bound, so M has to be greater than or equal to 1. Hence, M is greater than or equal to 1. Okay, so this is the first step. And then we'll show that M is less than or equal to 2. Okay, so next we show that m is less than or equal to 2. Okay, so well, proof by contradiction. Suppose m is greater than 2. Well, let a small number delta to be equal to m squared minus 2 over 2m. So this is going to be a positive number. Delta is greater than 0. This is because m squared is greater than 2, so m squared minus 1 minus 2 is greater than 0. And well, Okay, sorry, I just I don't know why my computer stucks. That's okay. So as I just now, I'm trying to show m is less than or equal to 2. We want to prove by contradiction, and suppose m is greater than 2. So we'll prove a contradiction. We'll let delta be less than m squared minus 2 over 2m. Okay, then we'll show m minus delta is in S. So if m minus delta is in S, then m cannot be a lower bound for S, which is a contradiction. So we'll just show first m minus delta squared. That's computed. This is equal to m squared minus 2 times m delta plus delta squared. Okay, so since delta, well, of course, let delta be greater than 0. Since delta is greater than 0, this one is greater than or equal to, is greater than m squared minus 2m delta. Because the last term, delta squared, is greater than 0. So when you throw away a positive number, you get smaller. And since delta is less than m squared minus 2 over 2m, so this quantity is greater than m squared minus 2m times m squared minus 2 over 2m. Then this is equal to m squared minus m squared minus 2, which is equal to 2. So what you actually showed is m minus delta squared is that is m minus delta squared is greater than 2. And next, we'll show m minus delta is greater than 0. And m minus delta itself is equal to, is greater than m minus m squared minus 2 over 2m. Because we are subtracting a larger number. And then this is greater than m minus m squared over 2m. But this is equal to m minus m over 2, which is m over 2 greater than 0. So actually what you showed is this number m minus delta. First, m minus delta is greater than 0, and m minus delta squared is greater than 2. So these two conditions tells you m minus delta is actually in S, because the definition of the set S is the set of all real numbers which are greater than 0, and the square is greater than 2. But this contradicts that m is a lower bound for S. since m minus delta is obviously less than m. Okay, this contradicts. This is a contradiction. All right. This means our assumption m greater than 2 is not correct. So m has to be less than or equal to 2. Okay, so we showed so m is less than or equal to 2. To show m is actually equal to 2, we have to show m is greater than or equal to 2. Well, again, proof by contradiction. Suppose m is strictly less than 2. And remember, we know that m is greater than 1. This is what we proved. This is already proved. Then we'll let delta be less than 2 minus m squared over 2m plus 1. Okay, so now we're going to show m plus delta is also a lower bound for s. Then we get a contradiction. Then we get a contradiction. So actually, what we need to show is m plus delta squared is less than 2. So this is equal to m squared plus delta times 2m plus delta. Okay, since if you look at this condition, delta is less than this quantity. Since m is greater than or equal to 1, the numerator is 2 minus m squared would be less than or equal to 2 minus 1 is 1 over 2m plus 1. So this is actually less than 1. So delta is also less than 1. So this is less than m squared plus delta times 2m plus 1, because delta is less than 1. And then we use our choice of delta, because delta is less than 2 minus m squared over 2m plus 1. So this is less than m squared plus 2 minus m squared over 2m plus 1 times 2m plus 1. So this is equal to m squared plus 2 minus m squared, which is equal to 2. So what we actually showed is m plus delta squared is less than 2. Now we want to show m plus delta is indeed a lower bound for S. Okay, so this, remember what we showed is m plus delta squared is less than 2. Okay, now for any x in S, we know that x is greater than 0 and x squared is greater than or equal to 2. So let's look at what is x minus m plus delta. So if we multiply this quantity by a positive number, x plus m plus delta. So if you remember, this is going to be the difference of squares. So it's equal to x squared minus m plus delta squared. So this is certainly greater than, because x squared is greater than or equal to 2 minus m plus delta squared. But since m plus delta squared is less than 2, this is going to be strictly greater than 0. In other words, we showed x minus m plus delta times a positive number, and x plus m plus delta is greater than 0. This implies x minus m plus delta is greater than 0. So m plus delta is the lower bound for S. But this is a contradiction. This contradicts that m is the greatest lower bound. Okay, because m plus delta is greater than m, it's also lower bound. So until now, we showed m is greater than or equal to 2, since m squared is greater than or equal to 2 and m squared is less than or equal to 2, we claim m squared is equal to 2. So you can see the greatest lower bound for set S is indeed what we want to prove. That is the real number which satisfies the square is equal to 2. Okay, so let's look at a few problems. So before we start the problems, let's review. We proved the Archimedean property, Archimedean principle. That is for any real number R, there is a natural number so that R is less than M. And then we also have the density theorem. The density theorem says for any real number A less than B, there exists a rational number between A and B. There is a rational number R so that R is between A and B. All right, now let's look at the problem. The problem is we want to prove that if A is a real number, then there exists a natural number so that A is less than 10 to the nth power. Okay. So, does anyone have an idea how to prove this one?
Would you be using the Archimedean principle to prove that?
Okay, we use the Archimedean principle and then?
And then at the end of it, you just set it equal. I mean, not equal, but set it less than. Well, you have to work it out first, and then you can set it back less to that to show that n is a natural number. I mean, n exists in a natural number, so that a is less than 0 to the n.
Okay, so essentially your approach is correct. Okay, let me write down what you want to say. So by the Archimedean principle, we know there exists some natural numbers, say m in n, or I directly write maybe n, say n in n, such that a is less than n. And then how should we proceed? Okay, so this is the statement of the Archimedean principle. You can find a natural number n is greater than a. What's next?
You divide both sides, so you take A to the right and N to the left, and you switch the inequality. So it'll be 1 over N is greater than 1 over A.
Well, you are saying you are taking reciprocal, but I don't think. If you take reciprocal, say for positive numbers, even for positive numbers here, you don't quite, you get what? You get 1 over, you get 1 over A is greater than 1 over N?
Yeah, 1 over A is, that. And then you will take the, I'm sorry, I'm driving at the same time trying to see this. And then you'll take the N.
Yes.
Oh no, I thought you had the other one. And then you'll make something where it has to be, the N, and then you'll take that and make that greater than the 1 over A greater than 1 over N, and then you use that to take the reciprocals again. Is that correct?
But the thing is that we want to prove this A is less than 10 to the nth power.
Okay, yeah, I didn't know that was a 10. I thought that was like a 0 to the N or something. I didn't see that 1 in front of it. So yeah, you'll take that 10 to the N, and you'll make that be greater than the 1 over A. Yeah, make that greater than that. Oh, you just erased it.
Okay, so I think the approach should be how to go from n to 10 to the n. So if we can prove n is less than 10, because a is already less than n. If we can show n is less than 10 to the n, then we are done. All right, so let me write it. If we can prove n is less than 10 to the n, then we get, since we have a is less than n, and n is less than 10 to the n, then we get a is less than 10 to the n. But if you look at this quantity n less than 10 to the n, this one is very similar to the problems we've seen before using mathematical induction. Okay, you can use mathematical induction to prove n is less than 10 to the n, and then combine this result with the selection of n, you get a is less than 10 to the n. Okay. then we get a is less than n would be less than 10 to the n. So now the problem is to prove n is less than 10 to the n. We use mathematical induction to show n is less than 10 to the n. Okay, so exercise for you. Okay, you just use mathematical induction to show n is less than 10 to the n. All right. Now let's look at another problem. We want to prove that for all n in n, all natural number n, there is an integer m so that so that 10 to the nth power times m is less than or equal to a, and a is less than or equal to 10 to the n times m plus 1. Okay, so a is between 10 to the nth power times m and less than or equal to 10 to the nth power times m plus 1. Okay, let's look at this inequality. So this inequality involves two integers. One is a natural number n, the other is an integer m. So since if there are two integers, then it's very difficult to handle. So somehow we want to rewrite this inequality in a way we only work for one integer. Since 10 to the nth power is a positive number, we can divide 10 to the nth power for this inequality, then you get a new equivalent inequality, okay? So if we divide 10 to the nth power, then the inequality we divide Okay, so just now when we divide when we divide 10 to the nth power, we get the equivalent inequality is m less than or equal to a over 10 to the nth power is less than or equal to m plus 1. Okay, so this is what we want to prove. So what we do is we by the Archimedean principle, we know that there exists a by the Archimedean principle. So for the number a over 10 to the n minus 1, well, we subtract 1 is to make it easier to directly choose n. There exists there is a k in n, a natural number k, so that a over 10 to the n minus 1 is less than k. So in other words, the set of upper bounds for the number a over 10 to the n minus 1 is is not empty. We use the property for natural numbers. Any long-empty subset of the natural numbers has a minimum. Okay. So the set of upper bound, the upper bound for this number a over 10 to the n minus 1 has a minimum in n. In n. So that is let just m be the minimum. Okay, let m be the minimum. All right, so m be the minimum. We certainly get a over 10 to the n minus 1 is less than or equal to m. So this implies a over 10 to the n is less than or equal to m plus 1. So on the other hand, since m is minimum, any number less than m cannot be an upper bound for this set in n. So m minus 1 would not be an upper bound. So this would be less than or equal to a over 10 to the n minus 1. So this implies m is less than or equal to a over 10 to the n. So if you combine these two inequalities, you get a over 10 to the n is greater than or equal to m. So this implies over 10 to the n is less than or equal to m plus 1. Okay, now let's look at another problem. This problem is look at the bottom is 6.22. So look at here, if we let S be the set of rational numbers so that R is equal to 10 to the nth power minus 1 over 10 to the nth power. Okay, so look at this set. What is this set of numbers? So if you let n be equal to 1, this R would be 10 minus 1 over 10. So it's 9 over 10. If we write this number in decimal format, then R is equal to 0.9. If we let n equals 2, then R equals to 100 minus 1 over 100, which is equal to 0.99. And if we let n equals to 3, then R is equal to 1000 minus 1 over 1000. So it's going to be 0.999. So in general, this set S consists of numbers like 0.9, 0.99, 0.999. So you keep going, okay? So you can have arbitrarily long nines for the decimal numbers, All right, so let's look at the question. The first one is we want to prove that S has at least one element. Of course, just now we were already plugged into n equals to 1, it has 0.9. So A is trivial. And B is we want to prove S has at least one upper bound. Okay, let me. So S actually is equal to this set, R equals to Q in Q, and R is equal to 10 to the n minus 1 over 10 to the n. And n is a natural number. So just now, what we write it, this is just 0.9. 0.99, 0.999, and you keep going, okay? So to prove S has the upper bound, this is clear. It is clear that if you take any number in S, this is 10 to the n minus 1 over 10 to the n. This is equal to 10 to the n over 10 to the n minus 1 over 10 to the n. Okay, this is equal to 1 minus 1 over 10 to the n. So this is less than 1. Less than 1. So 1 is an upper bound. Upper bound. And what is the least upper bound for S? So do you have any suggestion? What is the least upper bound for S? Y is also the least upper bound. But if you look at this number, what about this number? 0.9 repeated, which is equal to 0.999999. You keep going, this number. So if you look at this number, this is also a upper bound. Okay, if you have this two upper bound, and it's clear y is greater than or equal to 0.9 repeated. So what can we say? Y is the least upper bound, but this 0.9 repeated is also an upper bound, but this then implies actually 0.9 repeated is just equal to what? Okay, so now let's introduce another notation called Supremum and Infimum. So let S be a non-empty subset of the real numbers. subset of the real numbers. All right, so there are two cases. So if S has an upper bound, then we write the supremum, the sup of the set S, supremum, is equal to the least upper bound for S. Okay, the supremum of a set which is bounded above to be the least upper bound. And if S has no upper bound, then we write the supremum of S to be infinity. The supremum of S is equal to infinity. Okay, similarly, we can define the infimum. Okay, so if S has a lower bound, then we write the infimum, inf, of S is equal to the greatest lower bound. Greatest lower bound. And if S has no lower bound, then we call the infimum to be negative infinity. Then the infimum of S is negative infinity. All right, so let's use these definitions to work on a few examples. So find the supremum for the set A equals to the set of all real numbers n over n plus 1, where this n is a natural number. Okay, A is a set of all natural numbers, which is of the form n over n plus 1. So what does this set looks like? So if you let n to be equal to 1, so you get 1 over 2. And then if you let n equals to 2, you get 2 over 3. And if n equals to 3, you get 3 over 4. And you keep going. So to find out the supremum, you first have to determine whether the set A has an upper bound. So if you observe this pattern, you can see A certainly has an upper bound. For example, 2 is an upper bound. 2 is an upper bound. Okay, 2 is an upper bound. Now, since A has an upper bound, then the supremum is the least upper bound. So in this situation, what is the least upper bound? Okay, good. So 1 is the least upper bound. 1 is the least upper bound. So the supremum of A is just 1. Okay, just 1. Okay, now if we change the set B, say equal to the set of all 2m plus 3 over m plus 1. Okay, I'm not going to write down the numbers then. What is the infimum for B? What is the infimum for B? Okay, so I'll leave it as an exercise for you to work after class. Okay, you find the infimum of B. Well, a slightly harder problem is what is a supremum of B? All right, so since my computer gets a little bit problem, so you can see I have to change to another computer. It's kind of awkward to write, and we're going to stop it here. Do you have any questions? Yeah, in the next class, I'm certainly going to review some of the things, yes. All right. I'll see you next time.